Hello and welcome to today's video. Today we're going to be taking a look at a shift register to understand what it can do. In particular, I'm going to be looking at the 74HC595. Okay, it's an 8-bit shift register. So let's switch over to KiCad and take a look and see how we can use it. So here we have my typical prototype circuit board, and first things first, I'm just going to add in the 595 device. So as usual, the first thing I'm going to do is add in the power and the ground. Now you have to be a little aware when choosing the component. The 74 series, the 74 series typically runs at 5 volts. The 74HC variant will work at 3.3 volts. So that's the variant that I'm using here. Now, what exactly does this do? Well, first of all, this basically takes in data in the form of serial data and outputs it on a parallel format. So let's just hook this up and see what we can do. So if I first of all take a serial pin, I don't know what it's doing there. So let's hook a data line. It's being annoying. Okay, that's better. So we're going to hook up the serial line. Now there was another line called the serial clock. Let's hook that one up. And this R clock. And then we have the output enable, or the chip enable. Okay. So what actually is going to happen here is if we put a 1 signal on the this D12 line, and then I pulse the clock line, that 1 will then be shifted into the first register, in this case QA. If I then set the pin D12 to 0 and I operate the clock pulse, the 1 will move into B and the 0 will now be loaded into A. And we can keep doing this until we fill up the register. Now at that point we can toggle the R clock line, which will then take the data from effectively the shift memory and apply it simultaneously to the output. So a good example of this may be if you wanted to drive a 7-segment display. Now there's many different ways you can multiplex the lines and turning them on and off very quickly to pulse them, so it looks like all of the LEDs or segments are on at the same time, but in fact they are being pulsed. Or you could use this approach where actually all of the segments you want to be enabled will be enabled all of the time. And if you then want the microprocessor to be doing other tasks, it can be doing other tasks and the LED display will be fixed by the shift register. So it enables effectively outsourcing some of the data output tasks to a external chip. There are other types of shift registers. This one is a serial parallel output, serial SIPO, serial input, parallel output. There are other variants which will do a parallel input to a serial output, PISO, and we might look at those at another time. But this just is a way of getting data from a serial format to a parallel, or parallel data to a serial format, allowing you to do more with less pins. Now, another great thing about this chip is this pin called QH dash. This is a carry bit. So this chip has 8 outputs. If you wanted to do multiple, what you could very simply do is effectively QH to serial in, we'll tie the clock lines together and the output enable as well. Okay, this might get a bit messy. But you could do something like this, and you can concatenate as many of these together as you want. So now, again, with the few output pins, again, you don't even need to have the output enabled. If you're going to be using this all of the time, then you can just leave that enabled and free up another one of the pins from the digital I/O. So in some respects, you can think of this as a very simplified version of the I2C interface. It's not using encoded packets, but basically it's encoding data on a serial line with a clock pulse to control outputs. Okay, so that's pretty much what it does. I'm going to switch over in a minute to show you a demonstration on a prototype board, but I'm actually going to be building a project based around this and the Arduino, and maybe up to 10 7-segment displays. I just wanted to that will go into showing really what it does, but in concept, if you want to control or set digital output pins, and you have a limited number of I/O pins available on the microcontroller, this is just one way of expanding the amount of I/O pins that you have. So as I said, just remember, this is SIPO. So it's a serial input, parallel output. If you wanted to look at this in reverse, there is a 74HC595, I believe, which is a PISO, parallel input serial output, which basically does the reverse of this. It takes digital signals in on one side, then with the clock pulse it converts that back into serial data, which you can then read back in through 3 wires. Okay, so with that, I'm going to finish the KiCad part and switch over to a demo. Currently, what I've got is I've got 2 of these 74HC595 chips. I'm using the HC variant because the HC variant will work down to 3.3 volts. The other variants may only be work down to 5 volts. So it's just something to think of when you go to buy these chips. So what do we have? Well, for the time being, I'm just going to disconnect the second chip and turn it off. Okay, so we have the Arduino Nano. Now, fundamentally, what we have is we've got pin 16, which is VCC, and pin 8, which is ground, which is very typical. But then what we have is all of these pins coming over this side. So pin 15, 1 through 7 are the output pins. So they're the outputs that we're going to be using. Now, in 1650, pin 14 is a pin which is called the serial pin. That is where the data we're going to be using gets latched in to the chip. Then we have output enabled, which we have to pull low in order to enable the output. Then we have the R, they call it the R clock, it's the latching clock. And then we have the serial data clock, and then we have a reset line, and then there's one final pin, which is what we call called the inverted H, but it's the carry pin. When we want to connect multiple chips together, that's the pin which we're going to be using to connect into the serial input of the next chip. So anyway, so how does this work? So we have the clock line, the serial clock, which basically on a rising edge reads in the data, whatever's set on the serial pin. So that gets into the internal register, but it doesn't get set to the output until we clock and have a rising edge on the R clock line. So in order for this to work is we put the serial data in, we use the serial clock to bring it into the register, and then we invoke the R clock to latch it to the output. There also is a clear line which resets the registers inside the chip. So all I've got at the moment loaded is a simple sketch which basically clears the memory and then lights all of the LED outputs. So very clearly, it very simply works. Now, some things to watch out for are make sure that any outputs that you're not using are actually tied to the appropriate ground or VCC. You never want to leave any of these pins, inputs or outputs, floating. If you do, you can get some weird results. The other thing I noticed with this chip is the reset line. What you have to do to actually reset it, yes, you need to pull the line low, but then you actually need to do the R clock line as well to basically to clear the output memory as well. What I was seeing before is if I wasn't invoking the R clock line after doing the clear, I was still seeing junk data on the display. So anyway, you can see at the moment it comes up clean and it displays. Let me just put a let me just for fun open up the shift register. So this is a little sample program that I've put together. Nothing fancy. It's just basically pulses, and the line is to drive the clock signals. So here I reset, and then my demo basically is just a little loop which basically writes 1 into the first register, second register, and it does it for 16 registers with a 100 millisecond delay. And then every time we write a piece of data, or sorry, we clock a piece of data, and then we latch it into the display. So that way we can see the progression as we go through. You could change this to basically not latch it to the output until all of the data is written, which typically is more practically, that's how it would normally be used. Let me just go back to this reset. There's my reset here. So this is my reset, and then I'm latching it, calling the R clock line. So now I'm just going to do a reset, but I'm not going to latch it in. And then we can take a look and see what actually happens with this. Okay. It's a little bit hard to see. Let me just slow the this down, just to make it easier to see the errors. Now, okay, so here we are. It's going through. You notice when I reset it, it actually already had some data in the output. Okay, so it didn't, although the reset is being toggled, it's not actually writing that to the output until the next latch is sent. Which tricked me for a little bit. I was getting a bit confused exactly what was going on. So anyway, so we have that. Now, to connect up a second device, let me just power that off for a second. I've got linked across the serial clock line and the R clock line. These are the two main clock signals. Now, I'm going to link across the reset so that both this chip and this chip gets cleared. And I'm going to go back into the code and put in my latch statement again. So now, let me plug this back in, burn the sketch. Okay, so there we are. So this one's working now, but we're still not seeing anything. Now, that's because the serial data line has not been connected. Now, as I said, there's this QH inverted back here, which is the inverse of the QH signal being displayed here. If I connect that up there now, when this gets to the end, or when the register gets to the end of the line, it's going to carry over into the next chip. And I'm missing one more thing. The output enable pin needs to be pulled low. Oh, that's the problem. Okay. let's use this. There we go. Output enable pin is now low. So as you can see, we very easily have now those 4 wires here that are controlling this display, but also now controlling the next one. Now, as I said before, if we just keep these signal lines going down, we can connect up as many of these ICs as we want to drive as many different output signals as we want. So this is a very convenient way of really expanding the I/O, or in this case it's the O capability of the microcontroller. If you're using, instead of an SIPO device, you're using a parallel input serial output. It's basically the reverse of this, where you have a parallel input set which gets read serially. So with that enables you to actually have many inputs, digital inputs, going through into the 4 wires. So hopefully that gives you some idea of what the shift register can do. As I say, we're using it with the LED 7-segment display. It's a very standard use case, but there are many other practical applications for using a shift register such as this. One example I was thinking of, if you were doing like a fireworks display and you wanted to fire off 2,000 fireworks one after the other, you could easily use multiple of these chips in series, and then with a single command you can, and the clock signal, fire off each event at a specific interval from the next. So it's really down to your imagination as to what you can use it for. So with that, I'll go back to the desktop. Hi, I'm going to leave the video there today. I hope it's been of some interest. If you've got any questions, please feel free to put them in the comment sections below. But thank you for watching and have a great day.